Okay, great. Right, so yesterday I was explaining this Hodge state decomposition, and I think I wrote down the statement by the end of the lecture, and rather I wrote down the statement of the spectral sequence which we wanted. So let me just recall what it was. And if I write smaller, please yell out, because I was told yesterday I wrote smaller, but I was only told after somehow. So C is a complete and algebraically closed field. So it could be CP. I'm very hesitant to do anything right now. Sorry. Let's see, does this work? Okay, hopefully it won't happen again. Right, so C is a complete and algebraically closed field. X over C is some proper and smooth rigid analytic space. And we'll think of these in terms of adic spaces. And the statement is, I should have worn a button-down shirt. Right, so the statement is that there exists an E2 spectral sequence, which is the Hodge state spectral sequence, which looks like this. So the E2 term looks like hi of omega j of x with coefficients in differential forms. There's a Tate twist, and it converges to the étale cohomology. And so the goal of this series is to somehow try to convince you that this is doing something very non-trivial, right? So on the left-hand side, you have differential forms and with the slight Tate twist, and here you have étale cohomology. And what I want to explain to you is how differential forms and Tate twists naturally talk to each other. And what I want to do in this lecture is just do everything in one specific example. So I would like to spend this entire lecture focusing on the case of elliptic curves, and we'll try to understand what some of the maps in this spectral sequence look like and where they come from for elliptic curves. So that's the plan. But let me sort of say what the rough strategy of the global argument is going to be. So the strategy is going to be a two-step strategy. First of all, you construct some nice cover of X, which I will call pi. Let's say it goes from X infinity to X. And you try to study the Hodge cohomology of X infinity. So this X infinity will in fact be a perfectoid space. So you construct a cover by perfectoid spaces. And you try to understand the Hodge cohomology of perfectoid spaces, but one of the morals, which already Peter explained in his talk yesterday, is that if you're in this perfectoid setup, there is somehow no differential geometric information present. The cotangent complex vanishes, so anything coming from differential forms goes to zero, and so somehow the entire Hodge cohomology collapses to just cohomology of the structure sheaf, and it's somehow more understandable. And so use the theory of perfectoid spaces to analyze what's happening over here, and then in the next step you do the descent. So you descend your understanding back down to X. And then what will happen is that these differential forms, which had somehow vanished when you went up to this perfectoid world, will somehow make a reappearance in the descent procedure. And so today I want to just explain how this works out in the elliptic curve case. Okay. Right. Okay, so actually before I do that, let's do an easier example. So this is an example of something, of this procedure in action to understand something about fields themselves. So let's say you want to understand a fact about non-Archimedean fields, like QP, something about, say, the cohomological dimension. You can try to imitate this strategy to actually try to study them. So you first cover your field by a perfectoid field, use some theory about perfectoid fields to understand what's happening at the infinite level guy, and then come back down. And so here's an example of how this strategy works in practice. So say K over QP is some finite extension. And I'm going to write GK for the absolute Galois group. And then there is a theorem that the FP cohomological dimension of this Galois group is actually less than or equal to 2. So what I mean is that the cohomology with coefficients in p torsion shears vanishes above dimension 2. And so when I say p torsion, I mean p torsion, a finite abelian group killed by p with a continuous action of the Galois group. And so this is sort of a nice vanishing statement. It tells us that local fields somehow have a cohomological dimension 2. And how would you prove something like this using perfectoid spaces? So here's sort of a very vague idea of how the proof goes. So the strategy is you choose your cover x infinity, as I indicated over here, so the level of fields. You choose an extension, k infinity, sitting inside k bar. So you can choose this in such a way that this guy is perfectoid, well, after completion, because it's not complete. And the Galois group over here, so you can choose this to be Galois in such a way that the Galois group is actually just ZP. So a p-adic Lie extension with the group is ZP. So for example, K infinity could essentially just be the cyclotomic field. If you look at the cyclotomic field, you'll get a perfectoid extension where the Galois group is not quite ZP, but is off from ZP by a finite group. So those finite groups are order prime to P, and they don't really contribute to what happens with cohomology with P coefficients. So consider the setup. And then what we want to do is we want to understand something about K, or the absolute Galois group of K, in terms of what happens along either of these two maps. So the basic facts I'm going to input into this proof sketch are as follows. So the first fact is that the cohomological dimension of ZP itself, this group, is 1. And this is the very simple fact that if you're trying to compute the cohomology of an infinite cyclic group like ZP, or Z if you're working in the discrete setting, you can just compute the group cohomology by a two-term complex, the Koszul complex. And this is sketched in the exercises in my notes, how to do this. And so for any module, you would just write down a two-term complex which computes this cohomology. And so, of course, you're only going to have two non-zero cohomology groups. And so, yeah, this is all I'm going to say is explicit. We calculate. And so that somehow tells you that going from k to k infinity contributes 1 dimension. And so the question is, do you have only 1 dimension coming from k infinity to k bar? And the answer there is also yes. So the FP cohomological dimension of k infinity is also less than or equal to 1. And this is where you use the perfectoid theory. So as Jared explained, and then Skiran also explained, the absolute Galois, so k infinity, or rather its completion, is perfectoid. So its absolute Galois group is the absolute Galois group of a field of characteristic P, namely its tilt. And since we're only interested in questions about the absolute Galois group, we might as well move to characteristic P. So you use the tilting correspondence to reduce to an analogous statement in characteristic P, which is actually true in much more generality. So you reduce to the following proposition, which is that if R is any FP algebra, it could be a field like k infinity flat, but it doesn't have to be, then its étal cohomology with FP coefficients is actually equal to 0 for I bigger than 2, for I bigger than or equal to 2. And so in our case, if you take R to be k infinity flat, and so this will tell us that the cohomology of k infinity flat with coefficients in FP vanishes, but there's sort of a formal argument to go from the statement with FP coefficients to a statement with P torsion coefficients, which I don't want to go into, but this proposition is also explained in the exercises. The key point is to use the Arden-Schreier sequence. So the Arden-Schreier sequence, because you're in characteristic P, it allows you to relate the module FP with the structure sheaf on spec R, and the structure sheaf is something you understand the cohomology of very well. And so this helps you analyze what's going on over here. And so if you input these two facts into the Hochschild-Serre spectral sequence, that sort of solves the problem. So 1 plus 2 plus Hochschild-Serre. Then implies the theorem. Namely, that the cohomological dimension is bounded above by 2. And so I think this is kind of the babyest example of how you might use perfectoid spaces to analyze sort of more finite type objects, which is you first cover them by something perfectoid, use some theory about perfectoid spaces. In this case, the theory is the Artin-Schreier sequence, and then try to descend your understanding back down. And so what I want to do for the rest of the lecture today is explain how this works out in sort of a one-dimension higher example, so in the case of elliptic curves. Is that okay? So this was, I guess, section 1. So this is Hodge state decomposition for elliptic curves. And so I'm going to make some simplifying assumptions here, just to keep the exposition easy. So K, let's say, is my finite extension. And I'm going to work in the good reduction case just for simplicity. So script T over OK is going to be an elliptic curve with good reduction. Well, when I say script T over OK is an elliptic curve, that means it has the generic fiber has good reduction. So if you let E be the generic fiber, then it has good reduction. And as usual, C is going to be a completed algebraic closure of case A. And then the goal for today is to construct two maps, the two maps that go into the Hodge state decomposition. So the first map is the map relating differential forms to étale cohomology. So construct a Galois equivariant map, which I will call alpha, which goes from one forms on the elliptic curve to the Tate module, to the étale cohomology of the elliptic curve over K bar with coefficients in QP, tensored with C. But then if you remember the Hodge state decomposition, there was a twist on the I forms come with the twist of minus I. So if you move it over to the other side, the twist becomes a plus I. So we want a map like this. And we will construct this map explicitly using sort of something very special about the arithmetic of K. And the second map is the other one, is the one that's relating coherent cohomology of the structure sheaf to étale cohomology.
So in the first map, do you need to tensor on the left as well?
Right, so okay, sorry, I should have said this. So I have a map from a K vector space into a C vector space, so then I can also tensor on the left-hand side to get a map from this guy tensored with C into the right-hand side. So the hard part is to somehow construct this map. But yeah. And then the second map is to, so I guess I should say, so this is going to be following some ideas of Fontaine, part 1. And then the second map is relating the cohomology of the structure sheaf, so we'll construct also a Galois equivariant map, which goes from H1 of, H1 of E OE into H1 of the étale cohomology of the generic fiber, tensored with C. But now, since I'm doing zero forms, there's no twist. So it's just a map like this. But this map somehow, it's not going to use anything about the arithmetic, so this is going to instead use the construction that eventually gives us the Hodge state decomposition in general. So using perfectoid spaces. But I will not seriously use them, so I'll just say using inspiration from perfectoid spaces. What I will not do in the lecture today is check that these two maps actually give you the Hodge state decomposition. So it gives you maps from each, so it gives you the map that should be producing the Hodge state decomposition, but I'm not proving that that map is an isomorphism. So, yeah. Okay, I guess those are the goals for today, so I don't need to write what is not the goal for today. Is that okay? All right, so let's do this. So I'll need to assume certain facts about the cohomology of elliptic curves in order to do this computation. And I just want to recall them quickly. So this is just background facts I will use implicitly. So the first fact is something that I already mentioned yesterday, namely that the étale cohomology of an elliptic curve is computed in terms of its Tate module, or rather its dual. So H1 of EK bar with QP coefficients is the linear dual of the Tate module of EK bar. Oh, tensor QP. But the Tate module was the inverse limit of the p-power torsion points defined over the algebraic closure. And this, I should emphasize this. So this construction that takes this abelian group E of k bar and produces the Tate module makes sense for any abelian group whatsoever. You don't need any kind of assumptions on torsion or divisibility or anything like this. So the Tate module functor is a functor from abelian groups to abelian groups. And I will be applying it later to a different object. So I just want to emphasize this point. The second fact I want to recall is the valuator criterion, which everyone knows, but let me just write it. So since E satisfies the valuator criterion because it's proper, and so what that means concretely for us is that if you look at the C points, for example, the OC points of E are the same as the C points of Roman E. So any point defined over the generic fiber spreads out to a point of the integral model. So let me write this properly. And we will implicitly use this to identify the p-power torsion subgroups of the C points with p-power torsion subgroups of the OC points. And it will be important to have sort of an integral point rather than a rational point. The third fact I want to recall is that elliptic curves are Eilenberg-MacLane spaces, so they are k-pi 1s. And so what this means actually is something very simple. So it means if you compute the étale cohomology of the elliptic curve, again, over k bar with QP coefficients, that's the same as the cohomology of its fundamental group. So the fundamental group of the elliptic curve is the Tate module, and you can talk about the group cohomology of any profinite group like TP acting on QP in the trivial way. So this is continuous group cohomology. And the fact that elliptic curves are k-pi 1 implies the statement that the cohomology of this geometric object is computed by the cohomology of its fundamental group. So there's always a natural map for any value of E from the right-hand side to the left-hand side. And the assertion is that for elliptic curves, the map is actually an isomorphism. So for H1, for example, this is saying that H1 of the elliptic curve with QP coefficients is H1 of the Tate module with QP coefficients. But the way you compute group cohomology H1 is you just look at Homs out of the group into the target. So the right-hand side would be Homs from TP of E into QP, which is what I wrote over here in background fact 1. So this is just the version of that fact for a higher cohomology, which in this case just means H2. But I'm trying to do things in a way that also makes sense for arbitrary abelian schemes. So right, so these are essentially facts on the étale side, and then I need one fact on the coherent side, which is about how multiplication by an integer n on the elliptic curve acts on its coherent cohomology. So the multiplication by n map, which I'll denote by brackets n, going from E to E, induces n upper star, which goes from hi of E OE to itself. And this guy is actually equal to multiplication by n to the I. So n is the number you're multiplying by on the elliptic curve, and I is the cohomological degree. And so what this is saying is that pull back along multiplication by p, for example, acts by 1 on the constant functions, because pulling back constant functions keeps them constant. It acts by multiplication by p on the h1, and multiplication by p squared on the h2, and so on. Of course, there is no h2, so it's really just an interesting statement for I equals 1. And I think these are all the background facts about elliptic curves that I need. Okay, right. So let's actually get to the business. So what's the construction of this map alpha? So remember, alpha was supposed to be a map which is going from one forms on the elliptic curve to its étale cohomology tensored with C of 1. And so in order to do this, we really need a way to connect one forms with Tate twists. And I think this is somehow one of the Fontaine's key insights is that there is a good way to do this. And so this is what I want to explain. So we have this set up with fields. You have K sitting inside K bar, sitting inside K bar hat, which I was calling C. And so you can look at what happens on unit groups. So I have mu p infinity, which is the set of all p power roots of unity sitting inside, let's say, K bar, but it's actually sitting inside the ring of integers. So it's OK bar and OK bar star, because they're all units. And then what I can do is I can hit this with a certain map to differential forms. So here's omega 1 of OK bar, let's say over OK. So we are going to consider this rather weird-looking object, which is the differential forms of OK bar over OK. It turns out to be a good thing to do. And what is this map? So this map is the d-log map. It sends an element f to df over f. And you can easily check that this is actually a homomorphism. And so it is this map that's somehow going to play the crucial role of relating the left-hand side, which is sort of looking like it's related to étale cohomology, things like Tate twist, to the right-hand side, which is sort of related to differential forms. And the precise relation we need will be obtained by taking sort of Tate modules on both sides. So passing to Tate modules. So I can apply the functor of TP, of taking the Tate module, and then what you get is a map from ZP of 1, which is the Tate module of mu p infinity, into something I will call omega in the rest of the talk, and that's the Tate module of the right-hand side. And I will also call this map d-log, because it's simple that way. And so this is somehow the key glue that's connecting differential forms with the Tate twist. And what is Fontaine's theorem about them that's sort of getting things going is the following. So the theorem that Fontaine proved is that this map is essentially an isomorphism. Or rather, there's a precise way in which it fails to be an isomorphism. So, again, like Remy's question from before, the left-hand side is a ZP module. The right-hand side is naturally an OC module. So omega 1 of OK bar over OK is an OK bar module. So the Tate module is a priori an OK bar module, but it's actually p-adically complete, because Tate modules are always p-adically complete. And so it's a module with the completion of OK bar, which is OC. So you have a map from a ZP module to an OC module, and so you can just linearize it by tensoring with OC on the left-hand side. And so Fontaine says that that map is basically an isomorphism. So d-log linearizes to a map from OC of 1, which is just ZP of 1 tensored with OC over ZP, mapping into omega. And so it's not quite an isomorphism, but it is injective and the co-kernel is torsion. In fact, Fontaine proves more. So Fontaine proves that omega is actually a free rank 1 module. So this is just an inclusion of free rank 1 modules, and he explicitly tells you what the co-kernel is. It's if you have an inclusion of free rank 1 modules over evaluation ring, the co-kernel is just determined by its length. And Fontaine tells you that the length is something you can explicitly compute in terms of the differentials of the ground field OK that you started with. So for QP, it turns out that the co-kernel is scaled by p to the 1 over p minus 1. But the consequence for us is, if you invert p, then you get an isomorphism between C of 1 and omega. And this is somehow where the relation between Tate twists and differential forms comes from. So we're going to use this. And in my fourth lecture, I'll be talking about integral aspects of the Hodge-Tate comparison. This torsion co-kernel somehow plays a crucial role. It's sort of telling you the discrepancy between a Tate twist and a Breuer-Kissen twist, which hopefully I'll get to define in the fourth lecture. Questions about Fontaine's theorem? Okay, so let's now use this to define a map. So I claim that because of this, you actually formally get a map. So if you get a pairing, what? Ah, sorry, yes. Thank you. All right, so if you get a pairing which looks like so. So you can look at the OK bar points of E, of script E, which by the value criterion are the same as the K bar points of Roman E. And you can pair them against one forms on E. So H0 of my integral model with coefficients and one forms on the integral model relative to OK. And I claim that there is a natural pairing which takes values in omega 1 of the ground ring, so of OK bar over OK. And so what is this pairing? So the left-hand side is you have a map from spec of OK bar into E, and you have a one form, say omega, and you're supposed to spit out a one form on this ring OK bar, but there's the obvious thing you can do, which is pull back, and that's all you do. So it's X upper star of omega. And so this defines for you a one form on OK bar over OK, and so it gives you this kind of pairing at the level of sets, and you can check that it's actually bilinear. But I'm not doing it here. And so as a result, you get a map from, you get a relation between the two objects you were interested in. So this was page 6, 7. And so the map I'm going to write down is a map from the one forms, so H0, E, omega 1 of E over OK, maps to homomorphisms from E of K bar into omega 1 of OK bar over OK. And the construction is completely canonical, so it's equivariant for the Galois actions. So you actually end up with a Galois equivariant homomorphism from E of K bar to omega 1 of OK, bar over OK. And now you're in business, right? So now on the right-hand side, I can just apply the Tate module functor to get a map to Homs of GK into the Tate module of EK bar is by definition the Tate module of my elliptic curve. And over here, the Tate module of omega 1 was what I called omega. It was the definition of omega over here. And I can write this more canonically, or slightly differently anyways, as Homs over GK from TP of EK bar into QP, and then I pull out the tensoring with omega on the outside, because it doesn't matter. Sorry. And then by background fact 1, this side was something I understood in terms of the étale cohomology of E with QP coefficients. And so the whole thing becomes the étale cohomology of EK bar. I guess I need a ZP over here because I haven't inverted P yet. And so this is still a ZP, and this is still a ZP, tensor omega. But now I can invert P. And if I invert P, I get H1 of EK bar with QP coefficients, tensor omega with P inverted. But this is where Fontaine's theorem helps us. So Fontaine's theorem tells us that this is actually just the Tate twist by 1. And so therefore this gadget is the same as H1 of EK bar, coefficients in QP, tensored with C of 1. And so at the end of the day, you get a map from one forms on the integral model to the étale cohomology with the Tate twist of 1. But I mean, the right-hand side is a rational vector space, so I can just invert P. So it gives you a map from H0 of one forms on the elliptic curve over K into the étale cohomology with coefficients in QP tensored with CP of 1, and this was what the map alpha was. And so this is the construction of the map alpha relating one forms to étale cohomology. And as you can see, it sort of crucially relies on the fact that we have a relation between the differential forms on OK bar and the Tate twist of 1. And this is sort of the connection between differential forms on E and the Tate twist of Galois cohomology. And I'm not proving that this map is an isomorphism. So Fontaine gives a really nice argument for proving that this map is injective. he gives a really nice argument for proving this map is injective just in terms of formal groups. So essentially what you have to prove is that if you have a non-trivial one form on your elliptic curve, you can find a torsion point that's defined over a sufficiently ramified extension such that if you pull back to that torsion point, you get a really non-trivial differential for that ramified extension over OK. And so it requires a nice calculation, which I will not do here. So this finishes the construction of alpha. Yeah. This map? What was the question? Because this pairing is Galois invariant. You have to check that this pairing is Galois invariant, but I didn't make a choice, so. What else can it be? You're saying I screwed this up.
But actually, I think in the end it's okay.
Right, I think one of the isomorphisms is wrong. So I think this isomorphism is wrong if I put a Galois invariant. Right? So let me remove this over here, and say that this guy, this is GK equivariant by construction.
The right side has no Galois. Doesn't it map in?
So yeah, the left-hand side has no Galois action. So what Jared's pointing out is that the image of this map actually ends up inside the Galois invariants. Right. Yeah.
How do you root the GK and the twice the second isomorphism?
Which one? There's no GK, sorry. I forgot to delete one of them. Erase, scratch, cancel. Other questions about this map? Yeah.
Is it really true that that pairing is bilinear, or is it only bilinear after inverting P?
It's bilinear on the nose if I'm in the good reduction case, and if I'm not in the good reduction case, then it's bilinear after inverting P. So the point is that to prove that this pairing is bilinear, what you need is the property that if you have a one form on a group, then pullback along the multiplication is the same as pullback along the two projections tensored up together. So M upper star of omega is P1 upper star of omega tensor P2 upper star of omega, which is true if you're on an actual group, like I am. If you just have a model, which is a possibly bad model, then it will only be true after inverting a finite power of P. Other questions? Okay. So that was the first map. That was telling us how to go from one forms on the elliptic curve to a telecohomology. And actually, that map is enough to construct the Hodge state decomposition for elliptic curves. So if you look at Fontaine's paper, there's a nice argument using the dual elliptic curve, which gives you the other map. And you can then prove that you get an isomorphism. But I want to give a different construction of the other map, which is more geometric, which doesn't rely on the fact that I'm working over an arithmetically interesting field. It even makes sense over an algebraically closed field. Sorry, I should have made a remark, which is in my notes, which I didn't make. So this construction makes sense not just for elliptic curves, but any group. So it makes sense for GM. And since it makes sense for GM, what does it give you? It actually gives you a map from 8,0 of GM with coefficients in omega 1 of GM, let's say you're working over ZP, into H1 of GM over QP bar with coefficients in QP tensored with C of 1. But this is something we understood. So yesterday I explained why H1 of GM with QP coefficients is just QP of minus 1. And so I'm taking QP of minus 1 and tensoring it with C of 1. So the Tate twists cancel out, and you end up just getting a C. And this is canonically a C. So it has a distinguished generator. And inside here, you have a distinguished generator dt over t, where t is the coordinate on GM. And so an exercise for those of you that are interested or bored is to calculate the image. What number in C is it? Okay. Right. So now I can actually talk about the construction in the other direction, which is a geometric construction. So I'll call this map beta. And so I remind you what the setup was. Since the construction is geometric, I can forget about my base field K, which had some arithmetic structure, just work over the algebraic closure. So let me rename objects slightly to drop this annoying K bar subscript that was showing up. So fix E over OC now is an elliptic curve. And Roman E is the generic fiber. So I'm just reindexing my notation to replace K with C. And the goal is to construct this map beta, which is going from H1 of E OE into H1 of my elliptic curve, or sorry, E Q3 coefficients tensored with C in some natural way. And so this is where we use the inspiration coming from the perfectoid theory. So we consider one of the objects that showed up in Kiran's talk. So consider the inverse limit of multiplication by p on the elliptic curve. So let me call the first elliptic curve E. I have this multiplication by p map. I have the multiplication by p map, and so on. And I have this tower of schemes over OC, and I set E infinity to be the limit. And I don't want to do anything fancy, so I just work in the world of schemes over OC. This makes sense. Every time you have a tower of schemes where the transition maps are finite, you can just compute the inverse limit in the obvious way. On the affine charts, you take the direct limit of the coordinate rings, and that works out. So E infinity is going to be this object. And so as Kiran pointed out, this E infinity, or rather its generic fiber, gives a perfectoid space. And that's really what we are using, but it will be hidden in what I'm saying. And so in one of my exercises in the lecture notes, an argument for proving this fact is sketched using Frobenius and Verschiebung. But what we want to use is that we want to sort of input the group action here. So we're trying to construct a map from the coherent cohomology of E to the étale cohomology of E. We know that the étale cohomology of E is related to the Tate module, and so we need to bring the Tate module into the picture somehow. But it's already there when you sort of look at this. So observe that if you look at the multiplication by P map, or really the multiplication by P to the N map from E to E, this has a natural action but just by translation of EPN. Because, I mean, after all, this is a map of group schemes, and EPN is the kernel. So you can just translate, and it won't affect the map. And therefore, it also has an action of its C points, or its OC points, which are the same as the C points of the elliptic curve, P to the N torsion. And so for each transition map from level n to level 0, you have an action of the P to the N torsion points. And so when you pass to the inverse limit, you actually get an action of the Tate module on the inverse limit. So therefore, you get an action of TP of E on this inverse limit, E infinity, that is invariant or equivariant for the projection down to the bottom factor. So let me call this pi, and this is the bottom E that's showing up. So this E over here. So if you map from the inverse limit all the way down here, then translating by elements of the Tate module on the inverse limit does not affect the output. And this is sort of the crucial connection between the Tate module and something about coherent cohomology. I'm just regarding E infinity as a scheme, yeah. All right, so to make sense of this remark, I have to pass to the formal scheme first, and then this generic fiber. Sorry? I just mean it's equivariant for this map, so it's invariant. There's trivial action on the target, and there's an interesting action on the source, and the map intertwines them.
Why do you pass formal schemes and doesn't just local schemes?
Sorry?
You mentioned just then you have to pass formal schemes, but I thought you could just local schemes.
No, I was mentioning how to make sense of the remark, which is that it gives a perfectoid space on generic fibers, but the generic fiber functor factors through formal schemes. I was saying something tautological. Sorry. Right. So now we're trying to understand the coherent cohomology of this E, and we have a Tate module action over here on E infinity. So what is the picture? the picture is that you have E infinity, it maps down to E, or script E, we have this map pi, and we have this TP of E action here. And so we want to relate the cohomology of this object in coherent land to the cohomology of this group. And the connection comes from the following observation. So if you just pull back of functions, for example, it gives you a map from functions on your elliptic curve, h naught of E OE, or really, so you have to do it locally, to h naught of E infinity OE infinity. And since this map is equivariant for this group, the image is actually inside the invariance for the group action. That's essentially what it means for this map to be invariant for the group. But now, here I have a functor which is 8,0, which is 8,0 of something. Here I have another functor which is 8,0 something, and then I'm taking group invariance, which is also 8,0 in the world of group cohomology. So on the left-hand side, I have a functor for which derived functors make sense, and on the right-hand side, I have a composite of functors for which derived functors make sense. So you can derive the whole picture. Sorry?
Do we have a canonical admissible pair in this case, or some sort of
What is an admissible pair?
natural choice of resolution for these objects?
There might be, but I don't think it's relevant for what I'm saying. I'm just saying I have a natural transformation of one left exact functor to a composition of two left exact functors, and so I can derive it. But now, in order to keep my life simple and notation simple, I am going to work in the derived category. And so the derived category notation for cohomology is R gamma. So when you derive the left-hand side, you get R gamma of EOE. And if you sort of compute derived functors of a composite, Grothendieck tells you that there's a spectral sequence which goes from derived functors of each of the terms to the derived functors of the composite. In the derived category language, that becomes very simple. It just says you apply each of the derived functors one after the other. So the derived functors you apply are, first is the outer one. So it's the continuous group cohomology of TP of E. And then the one on the inside is just derived functors of global sections. So it's cohomology of E infinity. So you get some map that is potentially interesting that looks like this. Let me call this alpha 0. Beta 0. And it's sort of looking like it's in the right direction because we're trying to connect something about coherent cohomology to something about the étale cohomology of E, which is also something about the group cohomology of TP of E. Except there's this annoying term over here. We want constant coefficients, and instead we have this possibly annoying coefficient system showing up over here. But this is where the perfectoid theory, or some aspects of it, helps. So here's the observation, which is that these guys are actually very easily computable, and they turn out to be quite simple. So if you look at hi of E infinity with coefficients in OE infinity, then this is always, just by formal nonsense, the direct limit of hi of E OE along the transition maps. So pull back along multiplication by p. I had this tower, and the way this formalism works is that the cohomology of the inverse limit is the direct limit of the cohomologies of each of the pieces. So you're just doing pull back along p upper star of hi of EOE. But we know what the cohomology of the elliptic curve is. It lives in degree 0 and 1. In degree 0, it's the constant functions, and in degree 1, it's h1. But then I told you earlier how multiplication by p acts on cohomology. In degree 0, it acts as 1, and in degree 1, it acts as p. So in degree 0, you're doing nothing. So you just get h naught of EOE, which is just the constants, OC. And in degree 1, you get h1 of EOE, but then you're taking the direct limit along multiplication by p, which has the effect of inverting p, because that's how you compute localizations. And then it's 0 for I bigger than 1. And so this complex that we are trying to understand has cohomology groups that are quite simple. In degree 0, it's the constants, and in degree 1, it's some rational vector space. And there's nothing else. And so this understanding can help us. How am I doing on time? 5? Great, thanks. Right, so you learned in usual algebra that if you p-adically complete a module on which p acts invertibly, you get 0. And the same thing is true at the level of complexes in this derived world as well. So you can talk about a completion of R gamma of E infinity, OE infinity, and what it does is that it preserves the degree 0 part, because that's already complete, and it kills the degree 1 part, because it's already a rational vector space. So just formal nonsense about derived completions, which again I have a long exercise about in my notes, tells you that R gamma of E infinity OE infinity p-adically completed is actually just a single cohomology group in degree 0 and nothing in higher degrees. So it's quasi-isomorphic to OC shifted by 0. Essentially, you kill all the higher cohomology because P is acting invertibly and the degree 0 part survives. But this is useful for us. So we had this map beta 0, which was going into this annoying coefficient system, but then we can just map it further to the completion. So therefore, we get the following picture. We get a map from R gamma of E OE. We already had this map beta 0 to R gamma of continuous TP of E acting on R gamma of E infinity, OE infinity. I can complete internally, so complete the coefficient system to get a map to TP of E with coefficients in OC, because the completion of this complex is OC. But this is good. So by background fact, one of the background facts, this is actually just the cohomology of the elliptic curve with coefficients in OC, the étale cohomology. So more precisely, it's R gamma of E with coefficients in QP, it's R gamma of E with coefficients in ZP, and you tensor up to OC. So there's always some kind of base change like this where you can pull out the coefficient system when you have sufficient finite dimensionality. And this is in the étale world. So at the end of the day, we get this map from coherent cohomology to étale cohomology tensor OC, and then you just look at the degree 1 part. So in degree 1, this gives you a map from H1 of EOE into H1 of the elliptic curve with ZP coefficients tensored with OC. And this was the map beta that I was looking for, or really this guy with P inverted. And so this is the one way to produce a map from coherent cohomology to étale cohomology. And essentially what you do is you take your space, you cover it by something which is perfectoid so that all the cohomology dies. But then there's an interesting group action in this covering. And so the cohomology reappears when you try to do the descent, which in this case is showing up via this Tate module. So you're somehow pushing the coherent cohomology into something about the fundamental group, which feels like it's closer to étale cohomology. And so tomorrow I'll try to explain how this works in the case of a torus, which is sort of the key calculation that goes into proving the Hodge state decomposition for general smooth proper varieties. And I guess this is probably all I wanted to say, except I want to point out that, so I gave you these two maps, alpha and beta. Alpha was going from differential forms to étale cohomology, and beta was going from coherent cohomology to étale cohomology. And so I claimed that that gives you the Hodge state decomposition, but I didn't prove this. And I actually don't know how to prove this without going through the proofs of the comparison theorems and undoing what was going on. So I would be interested in knowing if that was kind of an elementary argument to see why the composite of these two maps is giving you an isomorphism. But I think I'll stop here. Thanks.
Questions for Bhargav?
Quick, what happens in degree 0? Anything interesting?
Well, in degree 0, the constants remain the constants, and that's where this OC came from.
Yes, got it.
So everything you told works for the case of an abelian variety?
Everything I wrote works for abelian schemes, yes. So in the good reduction case.
Ah, okay. Thank you.
Just following up on that question, so if in a general case, I still have this Hodge state decomposition for something that's not an abelian variety, you don't have the multiplication by p map, so is there any sort of maps like alpha or beta you can write down?
Are there any maps like alpha or beta that you can write down for general varieties? Well, I mean, the Hodge state decomposition tells you that there are such maps, but I don't know if there's explicit constructions of such maps. Essentially, each time you have a cover by a perfectoid space, you can go through the argument of the proof to give you a construction of such a map. And in some examples, it can be made pretty explicit, as I just did for elliptic curves. But I don't know if there's some general statement along these lines.
All right, let's thank Bhargav again.
We'll resume at 2:20.